All right, so we're going to talk today about absolute value equations. Tomorrow, then, that segues its way into talking about absolute value inequalities. Okay. So with the equations, you guys have done this before. What does absolute value of x mean to us? Any ideas? Any comments? Any?
How far away it is from 0.
Okay. The distance. In this case, x is away from 0. Okay? So that idea, the distance x is away from 0, the distance something is away from 0, gives me two things to think about, right? Can I be to the right of 0? Where else could I be? All right. So everything that we do, guys, everything that we do with absolute value equations or inequalities is going to have that aspect where we could be dealing with either side of 0. Okay? So we have to take that into account when we're solving our equations. Okay? And tomorrow are inequalities. So that's what absolute value means to you. So we're looking for the value of x right now. That will put that expression, 2x minus 5, 3 units away from 0, right? That is what that is saying to us. But 3 units away from 0 means that 2x minus 5 could be positive 3 when I plug in x, right? But what else could it be? It could be negative 3, okay? So here's the thing, and I want you guys to understand this. You're going to hear me say it all the time. We beat a dead horse with this, okay? When the absolute value bars disappear, okay, you gain simplification in regards to the equation by them disappearing, right? But you have to pay something for that. You can't just let them disappear and be left with 2x minus 5 equals 3 and solve that and be done. If that was the case, then what was the purpose of them putting absolute value bars in the problem to begin with, right? Okay? So when you remove the absolute value bars, there's a cost for that. The cost for that is that you need a second equation. And that second equation is going to be 2x minus 5 equals 3. But then you have to negate, you have to multiply one of your sides by a negative. It doesn't matter which one. Which one would be the easiest to multiply by a negative?
3.
The 3, right? Okay. But you can make the one on the left, negative 2x plus 5 equals positive 3, and gets the same result. Okay? But you need both those. Okay? Because both those equations are going to yield solutions that put our expression 2x minus 5 either on the left-hand side of 0 or on the right-hand side of 0. Okay? So solve those. It's pretty easy to solve. 2x equals 8. X equals 4, right? Okay. Over here, 2x equals what, 2? X equals 1. Okay. Those are the values that are going to tell me where the expression shows up on the number line. If I put 4 in, I get 8 minus 5, right? Is that a true statement? The absolute value of 3, 3? Yeah. But that put that expression, 2x minus 5, on the right-hand side of 0, right? It's positive. Okay. If I plug the 1 in, I get 2 minus 5 is negative 3, correct? Is the absolute value of negative 3 still 3?
Yep.
Yeah, but put that expression now on the left-hand side of 0. All right? But if I'm 3 units away from 0 on the left and 3 units away from 0 on the right, those distances are the same. I walk the same distance from 0 to both those. All right? You guys have seen that before, right? Okay. But one thing I want you to understand is that obviously you start with questions like that, but then they start getting more difficult. And I get something like this. Okay, I want to get rid of those absolute value bars, but that cannot be the first thing I do in a problem like this. It's just like when we dealt with square roots, we had to isolate, right? You need to isolate your absolute value. Okay? Isolate your variable before, your absolute value term before you start applying that rule that we just used. Okay? The kind of the generic rule is this: says if the absolute value of like ax plus b is equal to c, then you get ax plus b equals c, or ax plus b equals negative c. Okay, that's the rule. That's the generic rule for dealing with absolute value equations. If that's the generic rule, and we have algebraic proof of why we have to do this, and it has to do with that idea of distance, then we need to transform this example into something like this. Well, this has the absolute value all by itself, right? So we need to do it. There's no coefficient, there's no sum or addition or subtraction to that absolute value, so we need to transform this thing. So we're going to move 5 over. At the same time, I'll divide 3. I think we can do that. I should get x minus 7, the absolute value. Okay, if we move 5 over, that's 9, right? Divide by 3 gives me 3. Okay. Okay, so that is now getting my original equation into the format that the rule is presented in. Now I can apply the rule. Now I can say get rid of the absolute value and do that. But then I also gotta get rid of the absolute value. Need to pay for that. There's cost. Okay, so I gotta make that right hand side negative. I could have made the x minus 7 negative as well, but and leave the 3 as positive. That's usually a little bit more difficult and incorporates a little bit more work in this one. Add 3 to both sides. X is 10. Sorry, add 7 to both sides. Add 7 to both sides on this one. X is 4. And those are my 2 solutions. A lot of times, guys, when we write solutions that are finite, okay, meaning that I can count how many I have, right? We can count how many solutions we have here, right? Okay. The way we write that is we put a curly brace, we put a 4, we put a comma, we put a 10, and then another curly brace. Okay? And that tells us that we have a solution set that is finite. That's the way we do it. Okay. Yes?
So before you have to change it with the rule that ends or comes to like you like the x minus 7 equals 3 was not changed. Yeah. Because you didn't change it. But you said like if you take the absolute value off.
Right. When you take the absolute value off and you solve the equation that you get when you take the absolute value off. The cost of that then is you can't just be done there.
Like that can just figure out the answer.
Right. The cost of that is then you have to have this as well, and that is the idea of when the absolute values disappear, you can't. I mean, why have them if we're just going to let them disappear and solve the equation that way?
Does that have to be 410 or
I think it'd be 10-4, but usually we call that roster notation. So a lot of times we'll put them in order, but it doesn't really matter. Is that okay with everyone? All right. Let's go down to. This one's not too bad. Yes. Many of you are might going to say, well, this is just the way I would do this. I would move the 1 over and then move the 3x plus 6 and the absolute value to the other side. Is that okay? I think some of you are probably going to struggle maybe thinking about, well, this says the opposite of the absolute value. Just go ahead and do it this way. Go put 3 here, move that 1 over, and at the same time, I put that thing there. Okay? It says the same thing. If you're thinking graphically, guys, about what's happening, our linear absolute values, they look like V's, don't they? Okay? They look like V's, so we're looking where those V's intersect lines. Okay? Maybe they intersect other V's, maybe they intersect lines that have slope to them, maybe they intersect horizontal lines, but that's kind of what we're thinking about here. We're looking for those points of intersection. So this one we're just going to say 3 is equal to 3x plus 6. So that's the most obvious answer that people are going to get. Okay? A lot of times, every year I get 5, 6, 7 students that forget the rule, and they let the absolute value bars go away, and they get half the solutions. Okay? So your negative 3 is equal to 3x. X equals negative 1, right? Okay. But because the absolute value bars went away, I have to incorporate the second aspect. And the second aspect, again, is giving me that distance on the other side of 0 that this one did not provide me. Does that make sense? I don't know if that one gave me the one on the left or the right, okay? Because that's just the x value. I had to plug back in here and see which one it was. But if this one's one on the left of 0, the distance on the left is 0, then this one's going to be the distance that was on the right of 0. Does that make sense? Or vice versa. Subtract 6 from both sides. And then x ends up being negative 3, right? Those are my two solutions, negative 1, negative 3. There. I didn't put them in chronological order, but whatever. And then you can see if I put those in there, negative 1, what's the absolute value? What's 3 times negative 1? Negative 3 plus 6, 3. So I get 4 minus absolute value of 3, right? Does that give me 1? All right. So that's the value, that negative 1. Put this expression right here, this inequality or this absolute value part. It put that kind of on the right hand side of 0, correct? Okay. When I plug negative 3 in, I get again 4 minus then 3 times negative 3 is negative 9 plus 6 is negative 3, right? So that's the one that puts this expression here to the left of 0. But 4 minus the absolute value of negative 3 is still just 4 minus 3, right? And now I can get 1. So those two things satisfy, and we're good to go. Is that all right? Okay. The one style of problem that you're going to see that's a little bit different, a little bit harder to deal with, is this. And it's different because why? Two absolute values. Okay? Now people, they get shocked, they get scared, and they say, oh, 2 of them, I don't know what to do. You do the exact same thing. Okay? Basically what's going on here is saying that whatever this expression, whatever that distance is, okay, it's equal to whatever that distance is. So we could have, x, whatever x is, I can plug it, some x value in, and it's going to give me that thing on the left to be on the same side as 0 as that thing on the right. Does that make sense? Okay? So whatever, let's say here, let's put 0 here. Okay? There's some x value here that is going to take this thing, it's going to take that and put it right there on the right-hand side of 0, correct? And there's some x value that's going to take that thing right there and put it exactly right there. They're both on the same right-hand side of 0, right? But that x value might actually put them both on the left-hand side of 0. I just don't know. Does that make sense? But will they both still be the same distance away from 0? Yes. But there is also the situation, what if they're not both on the same side as 0? Could these two things be equal if that one is on that side of 0 and that one is on that side of 0? Yeah. Okay. Or vice versa. This one could be over there and that one could be over there. As long as those distances are the same, those would be true situations, right? So what we do with our work is going to show that this is when these expressions maybe show up on the same side as 0. And this is the work when they show up on opposite sides of 0. Okay? So this is how we do it. It's very well aligned with what we've already done. We take the equation that we start with and we just drop the absolute value bars. X minus 1 equals 3x plus 2. Okay? That's all we've got to do. And that's basically saying this is the situation where the x value that we're choosing is going to put those inequalities, those absolute values on the same side as 0. Okay? Let's go ahead and solve that real quick. If I solve that, I'm going to prove that point before we go on to the next thing. That minus 3 equals 2x. So what negative 3 halves? Negative 3 halves is equal to x. So that that value that negative 3 halves is equal to x. So let's put that back in up here. What's negative 3 halves minus 2 halves? Negative 5 halves. Okay? So that put that expression to the left, negative 2.5 units to the left of 0, right? Okay? Let's plug it in here. What's negative 3 halves times 3? Negative 9 halves, right? Negative 9 halves plus 4 halves, because that's what 2 is, right? Negative 9 halves plus 4 halves is negative 5 halves. Do you see that there put those two expressions both on the same side of 0? Because that negative 5 halves was consistent in both those? Is that right, everybody? So we've got the solution where they're both on the same side. But there is still a situation that one might be on the left of 0, one might be on the right of 0. So how do we obtain that? We say or, okay? So this is where they're both on the same side. Well, if they're on opposite sides, think about this. If I take 3, just the number 3, and I want to flip it over, I want to keep the same distance from 0, but I want to flip it across 0, how do I do that? Make it negative, right? You multiply by negative 1, okay? If I take 10 and I want to flip it across 0, but keep the same distance of 10 units, I multiply by a negative 1. So if I want to flip one of these across 0, what do I need to multiply by? Negative 1. Now, I only want to flip one of them, right? If I flip both of them, I'll get the same result that I got here. Okay? So what we're going to do is we're going to take x minus 1 is equal to now the opposite of 3x plus 2. And that's going to flip this one to the other side of 0. You could have multiplied the negative 1 through x minus 1 instead. It doesn't matter. I'm just the way that I've been taught and I do my work is I usually just let the right-hand side one be the negative. Sometimes if there's a simpler expression on the left, and maybe there's only one term on the left-hand side, maybe I'll multiply that one by the negative instead, okay? But generally speaking, it should not matter. Does not matter. Multiply that negative through. Okay, so now I'm going to add 3x to both sides. Gives me 4x. I will add 1 to both sides, so it gives me negative 1. X is equal to negative 1/4, right? Okay. Let's see what that looks like when I plug in negative 1/4 in. Negative 1/4 minus 1. Negative 5/4, right? Okay. Negative 1/4 times 3 is negative 3/4, right? Negative 3/4 plus 8/4. What's negative 3/4 plus 8/4? 5/4. And looks like it's negative. It should be positive. So there you see that one of those expressions is positive, one of them is negative. But if I take the absolute value of both of them, they both give me 5/4, right? Okay. So that's the practice that we need to go through. If you were a person, I just want to kind of show this to reiterate that it doesn't matter if I go negative x plus 1. So that would have been multiplying this side by the negative instead, right? Does that equal 3x plus 2? Okay, if I do that, add x to both sides. Okay, subtract 2 from both sides. Will I still get negative 1/4 for my x value? Yeah. Okay. If I multiply both sides by a negative, and hopefully if you were to ever do this, you go through the math and you realize it's redundant. Okay, add 3x to both sides, subtract 1 from both sides. What do I mean by redundant? What do I see? An answer I've already got, right? Okay, so you multiply only one side by the negative. You only want to flip one. Okay, does that idea, that concept kind of make sense? That's this heart, I think, of the absolute value questions that we're going to see with equations, is when they plug in 2 like this. They won't do anything in regards to adding or subtracting some value to those. We'll leave it. This will be the format that we see right now. Okay. If we have time, maybe later on, towards the end of the semester, in situations, some years, the end of the semester, we have maybe a week and a half where we can go back and talk about things in a little bit more detail. Some years it's been, the last day of class, we're wrapping up the last piece of information that we need to cover. And right now we're kind of behind right now. But if we have more time, at some point we come back and talk about maybe some more complex looking absolute value equations. Is that okay with everybody? Okay. The 1-7 assignment, make sure you get that done for tomorrow. There is a 1-8 open for like next week at some point. It'll be extended beyond what it's sitting at right now. It's what we're going to talk about tomorrow. We're talking about absolute value inequalities tomorrow. So that's something to think about as we prepare for tomorrow. Maybe a little activity tomorrow morning for about 5 minutes once class starts.
No, I like intervals.